We are back with another iteration. Let's start cracking the coding interview part 2. Sixth chapter, Big O. This is such an important concept that we are dedicating an entire long chapter to it. Big O time is the language and metric we use to describe the efficiency of algorithms. Not understanding it thoroughly can really hurt you in developing an algorithm. Not only might you be judged harshly for not really understanding Big O, but you'll also struggle to judge when your algorithm is getting faster or slower. Master this concept. An analogy. Imagine the following scenario. You've got a file on a hard drive and you need to send it to a friend who lives across the country. You need to get the file to your friend as fast as possible. How should you send it? Most people's first thought would be email, FTP, or some other means of electronic transfer. That thought is reasonable but only half correct. If it's a small file, you're certainly right. It would take 5 to 10 hours to get to an airport, hop on a flight, then deliver it to your friend. But what if the file were really, really large? Is it possible that it's faster to physically deliver it via plane? Yes, it actually is. A 1 terabyte file could take more than a day to transfer electronically. It would be much faster to just flight across the country. If your file is that urgent and cost isn't an issue, you might just want to do that. What if there were no flights and instead you had to drive across the country? Even then, for a really huge file, it would be faster to drive. Time complexity. This is what the concept of asymptotic runtime or big O time means. We could describe the data transfer algorithm runtime as electronic transfer O of S, where S is the size of the file. This means that the time to transfer the file increases linearly with the size of the file. Airplane transfer O of 1 with respect to the size of the file. As the size of the file increases, it won't take any longer to get your file to your friend. The time is constant. No matter how big the constant is and how slow the linear increases, linear will at some point surpass the constant. There are many more runtimes like this. Some of the most common ones are O of log n, O of n log n, O of n, O of n square, O of n cube, O of n 2 power n, etc. There's no fixed list of possible runtimes though. You can also have multiple variables in your runtime. For example, the time to paint a fence that's W meters wide and it's W h meters high can be described as O of WH. If you needed P layers of paint, then you could say that the time is O of WHP. Big O, big theta, and big omega. If you've never covered big O in an academic setting, you can probably skip this subsection. It might confuse you more than it helps. This FYI is mostly here to clear up ambiguity in wording for people who might have learned of big O before, so that they don't say, but I thought big O meant. Academics use. Just a sec. I want to make sure the stream's working. Oh, what do I have here? I want to. No, 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 no. No, no, no. No, no, no. Yeah. Reduce the volume a bit. The audio on the last stream was so bad. Anyway, let's get back to the topic here. You can also have multiple variables in your runtime. For example, the time to paint a fence. That's yes, already done. Oh man, no. Academics use big O, big theta, and big omega to describe runtimes. Big O in academia, big O describes an upper bound on the time. An algorithm that prints all the variables in an array could be described as O of n. But it could also be described as O of n squared, n cubed, or O of 2 power n. The algorithm is at least as fast as each of these differ. There are upper bounds on the runtime. This is similar to less than or equal to relationship. If Bob is x years old, then you could say that x is less than or equal to 130. It would also be correct to say that x is less than or equal to 1000 or x is less than 1 million. It's technically true. Likewise, a simple algorithm to print the values in an array is O of n, or as well as O of n cubed for any runtime bigger than O of n. Big omega. In academia, omega is the equivalent concept, but for lower bound. Printing the values in an array is omega of n as well as omega of log n and omega of 1. After all, you know that it won't be faster than those runtimes. So big O is the upper bound, big omega is the lower bound, big theta is both O and omega. That is, an algorithm is big theta of big theta of n if it's both big O of n and omega of n. Gives a tight band on runtime. Best case, worst case, and expected case. We can actually describe our runtime for an algorithm in three different ways. Let's look at it from the perspective of quicksort. So big O gives the upper bound, big omega gives the lower bound, big theta gives both of them. Let's look at this from the perspective of quicksort. Quicksort picks a random element as a pivot and then swaps values in the array such that the elements less than the pivot appear before the elements greater than the pivot. This gives a partial sort. Then it recursively sorts the left and right sides using a similar process. Best case, if all elements are equal, the quicksort will on average just traverse through the array once. This is O of n. Worst case is O of n squared. Expected case O of n log n. We rarely discuss best time complexity because it's not a very useful concept. After all, we could take essentially any algorithm's special case some input and then get an O of 1 time in the best case. For many, probably most algorithms, the worst case and the expected case are the same. Sometimes they're different though, as we need to describe both the runtimes. What's the relationship between the best, worst, and expected case and big O, theta, and omega? It's easy for candidates to muddle these concepts, but there's no particular relationship between the concepts. Best, worst, and expected cases describe the big O or big theta time for particular inputs or scenarios. Space complexity. Time is not the only thing that matters in an algorithm. We might also care about the amount of memory or space required by an algorithm. Space complexity is a parallel concept to time complexity. If we need to create an array of size n, this will require O of n space. If you need a two-dimensional array of size n into n, this will require O of n squared space. Stack space and recursive calls counts too. For example, code like this would take O of n time and O of n space. Each of these calls is added to the call stack and takes up actual memory. However, because you have n calls doesn't mean it takes O of n space. Drop the constants. I will come back. Just a sec. Okay, it's very possible for O of n code to run faster than O of 1 code for specific inputs. Big O just describes the rate of increase. For these reasons, we drop the constants in runtime. An algorithm that one might have described as O of 2n is actually O of n. Many people resist doing this. They will see the code that has two nested for loops and continue this O of 2n. They think they're being more precise. They're not. Consider the below code. Which one is faster? The first one does for loop and the other one does two for loops. But then the first solution has 2 lines of code per for loop than one. If you're going to count the number of instructions, then you'd have to go to the assembly level and take into account that multiplication requires more instructions than addition, uh, how the compiler would optimize something, and all sorts of other details. This would be horrendously complicated, so don't even going down this road. Big O allows us to express how the runtime scales. We just need to accept that it doesn't mean that O of n is always better than O of n squared. The constants might be bigger, it seems. Drop the non-dominant terms. What do you do about an expression such as O of n squared plus n? That second n isn't exactly a constant, but it's not especially important. We already said that we drop constants, therefore O of n squared plus n squared would be O of n squared. If we don't care about that latter n squared term, why would we care about n? We don't. We should drop the non-dominant terms. O of n squared plus n becomes O of n squared. O of n plus log n becomes O of n. O of 5 into 2 power n plus 10,000 n per 100. Two power x is very big. Multi-part algorithms, add versus multiply. Suppose you have an algorithm that has two steps. When you multiply the runtimes and when you add them, this is a common source of confusion for the candidates. In the example on the left, we do A chunks of work and then B chunks of work. Therefore, the total amount of work is O of A plus B. In the example on the right, we do B chunks of work for each element in A. Therefore, the total amount of work is O of A into B. In other words, if your algorithm is in the form, do this, then you're that. Okay, yeah, let's go. Amortized time. Oh, amortized time complexes. We had this in advanced data structures. An array list or a dynamically resizing array allows you to have the benefits of an array while offering flexibility in size. You won't run out of space in an array list since its capacity will grow as you insert elements. An array list is implemented with an array. When the array hits capacity, the array list class will create a new array with double the capacity and copy all the elements over to the new array. How do you describe the runtime of insertion? This is a tricky question. The array could be full. If the array contains n elements, then inserting a new element will take O of n time. You will have to create a new array of size 2n and then copy n elements over. This insertion will take O of n time. However, we also know that this doesn't happen very often. The vast majority of time insertion will be in O of n time. We need a concept that takes both into account. This is what amortized time does. It allows us to describe that, yes, this worst case happens every once in a while, but once it happens, it won't happen again for so long that the cost is now amortized. In this case, what is the amortized time? As we insert elements, we double the capacity when the size of the array is power of 2. So after x elements, we double the capacity at array sizes 1, 2, 4, 8, 6 to x. The music is too loud. That doubling takes respectively 1, 2, 4, 8, 16 x copies. What's the sum of that? If you read this sum left to right, it starts with 2x. Therefore, x insertions take O of 2x time. The amortized time for each insertion is O of n. Log n runtimes. We commonly see O of log n runtime in runtimes. Where does this come from? Let's look at binary search as an example. In binary search, we're looking for an example x in an element sorted array. We first compare x to the midpoint of the array. If x is middle, then we return. Yeah, that's binary search. This is the same reason why finding an element in a balanced binary search tree is log n. With each comparison, we either go left or right, have the nodes are on each side, so we cut the problem space in half each time. Recursive runtimes. Here's a tricky one. What's the runtime of this code? A lot of people will, for some reason, see the two calls to f and jump to O of n squared. This is completely incorrect. Rather than making assumptions, let's derive the runtime by walking through the code. The tree will have depth n. Each node has 2 children, therefore each level will have twice as many calls as the one above it. The number of nodes on each level is this. Therefore, there will be 2 power n plus 1 minus 1 nodes. Try to remember this pattern. When you have a recursive function that makes multiple calls, the runtime will often look like O of branches power depth. In this case, this gives us O of 2 power n. The space complexity will be O of n. Oh, there are examples. Big O time is a difficult concept at first, however once it clicks it gets fairly easy. The same patterns come up again and again and the rest you can derive. We'll start off easy and get progressively more difficult. What's the runtime of the below code? Oh, there's a lot of examples here. There's a lot of examples here. I want to do this example sometime, because without doing examples it doesn't matter. Yeah, I'm gonna stop recording here. This was a good little period we had. Alright, I'll be back with the next video in a while.